we had one or two classes on norms, but actually I never formally defined the definition of norm, right? So this is the formal definition of norm. So what did I write? Let X be a metric space. Why do you need a metric space here? Because the moment we talk about the norm, that means we are discussing about how to quantify a signal or a vector or a matrix. Then quantifying a vector or matrix or of any of these elements or objects, what does it mean? That means we are trying to quantify either its length or size or power or strength, whatever may be. So that's why whatever underlying space you consider, whether you are consider a space of vectors or a space of matrices or a space of signals, it must have something, that it must have another measurable function which will quantify its strength or something that. So metric space means underlying there is a space, and along with that there would be a function that is which will evaluate the strength or the power, or like let's say example, that is when we talk about the vector space. In vector space it is not only about the object, it is equipped with, that is first of all like norm, it can be an inner product or some other things like. So that's why here the X is a metric space. Okay. Otherwise I could have simply write that is X be any space, that means any topological space. But here we are definitely considering a particular space which is a metric space. That means a metric must be there for quantifying the strength, power or like anything of that, the underlying object. So X, it can be a vector space, it can be a metric space, matrix space of matrices, it can be a function space, it can be a space of a complex functions, right, which later we talked about the Hurdy space. And a norm is a real valued function, that means the norm, it is always real valued. Not only that, it cannot ever be negative, it is always a non-negative quantity, right, denoted as, this is the symbol for the norm, from X to R. X is the space for whose, like this is the kind of object on which we are going to evaluate the norm, and ultimately it will produce a real number. So that's why it is a mapping. Like if you wish to define it as a function, the norm as a function, then it is a function from that metric space X to the R plus, okay, which satisfies the following four properties. What are the properties? That is, norm is always non-negative, the first one. Then if you find the norm of an object is 0, if and only if that object is identically equals to 0. Okay, that means suppose if you have a vector, suppose X is a vector, you have the element small x1, small x2 up to small xn. Then somebody tells you that okay, Euclidean norm of this vector is 0. Now you think about the situation, like Euclidean norm means this is root over x1 square plus x2 square up to all of the xn square. Okay, so in that case, each of them individually, x1, x2 up to xn, individually it has to be 0. Okay, is it clear? Now immediately you can ask me that is, sir, okay, like this is the best case you have considered because all of them are square. What happens if this is a 1 norm? It is about 2 norm. Let's say if it is a 1 norm, then what will happen? Here also the same thing, since we are taking the absolute value, so absolute values of all the summation of absolute values of all the entries, that is equals to 0. That means each one of them has to 0, right? So that is the meaning of the second one. Third, if you just multiply that object, whether vector or matrix, by a scalar, it can be real or it can be complex, then it is simply the norm of that unscaled vector or unscaled norm of the unscaled object multiplied by the magnitude of that, or simply the absolute value or magnitude if it is a complex. Okay, so that's why it is a only that is inside one pair of bars. So this is, if this is alpha a complex number, then it gives you the magnitude. If it is a real number, then it is the absolute value, okay, and the norm of the original object. Okay, this is about the third one. And the fourth one, this is about triangle inequality. Triangle inequality means that is, if you take a triangle, then always the sum of the two side length of the sum of the lengths of the two sides is always lesser than equals to Exactly. So that is about the triangular inequality. That is also satisfied by all the norms. Now, if you have the matrix, for matrices there are some induced norms. Like today, that is immediately after that we will start matrix norm. In matrix there are some of the norms which are non-induced, some other norms which are induced. Now for all induced matrix norms, it satisfies this multiplicative property as well. This is either called triangular inequality or the sum rule, and this is the product rule of norms. Okay, this is not exhibited by the vectors. This is exhibited by matrices and some other objects. Okay.
So that Euclidean norm of x should be equal to mod of x1 square plus mod of x2 square.
Here that I didn't write the mod because anyway we are taking the square value. But if you connect it from this P norm formula, then that is we can go to that.
Because otherwise, then if a matrix is column vector is I and 1, then it should be 0 without being all the matrices 0. Without,
but here we are, if it is a Euclidean norm, I mean the 2 norm, in that case all the elements are squared valued, right?
yeah. But
So even if you use the absolute value,
with absolute value it's right, but without that mod, if a element is I and then another element is 1, then I square plus 1 square, that means it is becoming 0 without.
you are right. That is if you, because I remember that is when I defined that norm, then I did it for the when the underlying field was real. But if the underlying field in that sense I said, but really that is if you consider that your x, suppose it is the vector, it belongs to Cn, then definitely you need a magnitude over here. Is it clear for all of you? Please don't get confused. That when I defined maybe last class or even last to last class, that is I said while defining the 2 norm, that is whether you put this absolute value here or not, both of them will remain the same. That is with respect to when the underlying field was real. That means I consider for all x this is actually Rn. But the moment you consider the field to be C, then here you have to genuinely use that, what should I say, this is magnitude. Okay. Now the definition what I have written, that is with respect to the generic sense. Here when I am talking about this metric space, then metric space like over a field. Now that field can be R, that field can be C. That is in short, we write X in bracket K. This K means it is either R or it is C. Is it fine up to this much? Let's directly move on to the matrix norm because I believe it was last day I didn't have. Since I use this term matrix space over here, few things I am writing, that is you can check it on your own. That is, one is a these things are actually part of functional analysis, but anyway in control, whenever we try to learn control theory, they are automatically they come. Now here we are dealing with non-linear spaces, right? Metric space, here the norm is the metric. What is the meaning of metric?
Measure.
Exactly. Some technique by which you can measure the thing. Now, which kind of measurement, that we don't know. But here we are talking about the measurement in the sense of either a length or a size or an amplification power, energy, something like that. So here the metric space, those we are considering, it is a normed, if you say that we are considering normed vector spaces. Okay, so in that sense I wrote non-linear spaces. So they are a particular metric space. Now there are another kind of spaces which is an inner product space, that means for which the inner product is defined. Non-linear spaces means the vector spaces which we are considering, whether vector or space of matrices or functions for which the norm is defined. So usually we write in a big bracket x comma the metric. Now this is a non-linear space, okay? Of course this is a metric space. If I simply write x comma a d, this is an example of a metric space where the x is the underlying space and d is the metric. Here I have considered as if the metric to be distance, the small d for distance, okay? The distance is the most common type of metric. So that's why if you write in a pair, that is always that you can ask the sir, why you are writing now in a pair? Because it is not only about the space, you are also specifying a measuring technique, a measurement, which is the metric. So here d for distance, that is the metric in this case. In the first case, this is norm, here norm is the metric. So all of this is a non-linear space, this is a metric space, but non-linear space is also a metric space. Now suppose if we simply talk about the x, this is a space, then we will call it a topological space. We are not specifying any kind of metric, okay? That is the difference between these two. These few things you learn on your own, search a little bit on internet, they will really help you later. Now is Banach space. This is the name of after a great mathematician, Stephen Banach. Banach space is a nonlinear space. Another one, Hilbert, that is also after the name of a great mathematician, David Hilbert. The Hilbert is after this Hilbert space is also that is an example of an inner product space. Now for Hardy, that is we can define both. Norm also exists as well as inner product also exists. Okay. Now for like if somebody asks me, sir, what is a non-linear space? Then if you have to define the not non-linear, but that's for Banach space, Hilbert space. If somebody asks you that is why these spaces are particularly you are mentioning, then this complete type of space, that keyword will come. Now the question will come, what is a complete space? In that regard I wrote completeness of a space. When you will check the definition, immediately there you will find the definition of completeness has been given with respect to a particular type of sequence which is called Cauchy sequence. So that's why in that regard I have written all of them. And Cauchy-Schwarz inequality, that is true for any object coming from an inner product space, not from nonlinear space. Once again, Cauchy-Schwarz inequality. That Cauchy-Schwarz inequality means like suppose you have two objects x and y. This is called absolute value of the inner product. that is lesser than equals to the norm of x into norm of y. This is called Cauchy-Schwarz inequality. And now for all xy belonging to x, where x is the inner product space. Sorry, I should have been ideas. This doesn't exist for non-linear space, so we need something more. That is, you know the inner product, right? Suppose you have two vectors, then x and y, then x1, x2 up to xn, y1, y2 up to yn. That is inner product means, suppose I am writing it is x star y. X star y means that is x1 star, x2 star up to xn star. That is for x star, and then your y. So y1, y2 up to yn. So ultimately that is when you are doing the x1 star into y1. So that is basically this I equals to 1 to n xi star yi. This is called the inner product. You already did it in case of vector, but now this is not only for vector, it can be for other matrix spaces, I mean for other inner product spaces as well.
So if
Now,
you have inner product of two matrices, then it means if A inner product with B, that means A transpose B should give us the inner product.
Now there is a case of the space of matrices, whether that is the inner product space, because matrix product, that is not an inner product, right? For vectors, inner products are defined. For function also we can define similarly. But for matrices, whether that type of multiplication exists or not, that we don't know. Is it fine? Let us move on to the matrix now. Did you ever come across these terms while you had linear algebra?
Only in inner product we have
Not about the other thing like Banach or Hilbert.
Cauchy-Schwarz
Cauchy-Schwarz.
we but other than that we want.
first of all, sum
What is the
induced matrix norm,
in the 6th point?
induced infinity norm, either INF or infinity. One by one we will learn sum norm. If A or G, whatever, last day what the symbol we considered? M. You can write even MI. Probably I know small a, right? For most of the notations I write small a. Here I have to then write small ij. This is sum norm, and why is quite related to the vector 1 norm. There also, that is, we calculate the summation of all the absolute values, right? So in that way it is similar to vector 1 norm. Then Frobenius norm. It is analogous to the what? Euclidean norm. So in case of vector, what the way we define the Euclidean norm or 2 norm, here also we are going to do exactly the same. Okay. It can be proved that the same thing is there for Rudolph stress of this can also be proved as summation of this region we are getting clumsy, so that's why I have it is. Now can you see the similarities between a vector 1 norm and matrix sum norm, then vector 2 norm or vector Euclidean norm, matrix Euclidean norm, then vector max norm or sup norm and matrix max norm or sup norm. Okay. Now please note that this maximum norm, this doesn't satisfy the triangle inequality. So that's why it is not a standard maximum norm. But sometimes it is required to find out that this could be the maximum of all other norms. Like later you will find a relation where all the matrix norms, they will be in between the spectral radius and the maximum norm. So that bound is really required for us. That is what I wanted to say. That is later you will find the relationship this is the spectral radius lesser than equals to any of the matrix norm, and that is again lesser than equals to this max norm. At this moment I am putting a star verified. Since I have written the spectral radius, what is a spectral radius? Maybe it can be other way, like all this one is lesser than equals to vector radius and then greater than equals to some other. So that's why I don't verify. Okay, this I will check. In fact, this is there is suggested. I'm slightly forgetting this one. I will check it out. Now, since I have introduced the notation spectral radius, what is the spectral radius? How do you define?
So max eigenvalue.
Not max eigenvalue. Max of the no, max of the eigenvalue, but of the absolute. This is the spectral radius. Okay. Again, spectral radius is not also a matrix norm. Although it is a good bound, it is used somewhere while considering or while evaluating the robustness, but still it is not a matrix norm. Now coming to the induced norm. Huh.
I may be wrong, but this is your Bluetooth. Because trace of m star m is summation of sigma I square.
So you are saying the root would be inside.
So this, for the last one, should there be a root overall?
Possible. I will check it. Let me check. I am slightly forgetting. It can be. It can be. You are correct. Yes, here we should have view. Thank you very much. Yes, I missed that point. It must be a square root. Okay, this is the relation. At this moment, we are not doing the proof, but the proof is also available. Not in Fogested book. In mathematics book, the proof is available. But the other relation which I wrote, that is correct. I think that is the lower bound is the spectral radius, and the upper bound would be the maximum norm. Okay. And one more thing, that is, I said that is this max norm. This is not a standard maximum norm because this won't satisfy the multiplicative property. Probably I mentioned it won't satisfy the triangle inequality. No, it will satisfy the triangle inequality, but this one not. Okay? Now coming to the induced norm. Can anybody tell me that is what is the induced quantity? That means you are getting something by the influence of something else, right? That is, there is one thing has induced something, like electromagnetic induction. When you get a current, or like due to a change in magnetic field, or even due to a change in magnetic field, voltage can be induced. Okay, so here, if something is that, like suppose you have already got the vector norm, 1 norm, 2 norm and infinity norm, and then by vector norm, if we can get a matrix norm, that would be called an induced matrix norm. Are you getting? if I say that it is vector norms will induce a matrix norm, that means from based on the vector norms, if we can define a matrix norm, then it will be called an induced matrix norm. What is the concept? Like suppose you have a matrix G or M, whatever you consider. This is the input vector U, this is the output vector Y. Now if somebody asks you that Y equals to GU, fine, what is the gain? The moment we hear the term gain, that means we are trying to find out the ratio of the output to input, right? Now the output, that is a vector, input, that is a vector. Like if it is a scalar, you can simply divide the output quantity by input quantity. But it's a vector. Certainly you cannot divide a vector by another vector. So then we need a metric, right? Here there is a genuine requirement of a metric. So then if somebody asks you that is what is the gain or amplification factor of that matrix, then what you will find? In that case, suppose I am writing the norm of G. So this norm, it will quantify the gain, okay, or the amplification power of that matrix, okay. It can be system. In fact, that is the same concept will be applied to H infinity norm, what we have already studied. So here, see, it's a matrix norm, okay. Now that will be the ratio of the norm of the output vector by norm of the input vector, okay. Now that is when you are defining it is a norm, then that is you have to find out the maximum gain that is produced by this matrix. So here you have to write the maximum over all U, right? But in that case it would be then choice would be over the infinite choices. So that's why how do you write? The symbol is like this, I comma P. That means P means matrix P norm and I comma means induced matrix P norm. Okay. In that sense, this norm symbol and then in the suffix it is I comma P. That is equals to maximum over the norm of the input signal U, and which now we are going to take with respect to closed ball lesser than equals to 1 to restrict our search within a known space, because otherwise it would be an infinite search problem. First of all, that is what we write the max of this. Equals to at this moment it will be a bit hazy to you because we are not learning the proof, but all of them can be proved by using functional analysis techniques. So in this way we define the induced matrix norms, okay. That is nothing but how you quantify the amplification power of a matrix. Here, that is one thing I have missed everywhere. I should have written the P. That means that vector P norm is giving rise to that matrix P norm. If it is vector P norm 1, that is if it is the vector 1 norm, then it would be G I comma 1. If it is 2, G I comma 2, similarly. So here the vector P norm is inducing the matrix P norm. So that's why here it is called the induced matrix P norms. Okay. H infinity?
The
If when we will go to the system norm, so there is this infinity norm that is also induced. Now can you tell me that is induced by which norm? So if instead of a matrix, if this is a transfer function matrix, then there is an input, output, of course. Here this is all of them is a constant. That is u, y, that is a constant vector. That is g is a constant matrix. Now I said that is if instead of the constant matrix, if you have a transfer function matrix, then what will happen? In that case also it would be an input vector, output vector, but that is not a constant vector, rather that is a vector of functions, right? So then that is which norm will induce the H infinity norm? No, in that case, like here I said that the vector P norm will give rise to these induced matrix norms. Now, if that matrix is a transfer function matrix, then what about these norms? Then it is not the component input or output, that is not a constant vector. What is that? It is a signal. For signal, which kind of norms we deal with? L norms, capital L norms. So in that there it would be that is L1, L2, L infinity. Matrix induced one norm means it is with respect to the vector one norm. If it is two norm, then with respect to the vector two norm. If it is infinity, then with respect to the vector sup norm or max norm. Okay. Now that is for this induced two norm. It has a nice expression or nice quantity associated with that. This is also called spectral norm. Why spectral term has come up, that will be clear to us later. Spectral theory, there is something that will come. Some part of spectral theory will come into the lowest control. Then it will be clear. That is why this is called spectral norm. So now can you see that is both this induced two norm and Frobenius norm, they have direct connection with singular values. This induced two norm, that is nothing but equal to the maximum singular value of a matrix. Right? If it is a Frobenius norm, this is a square root of sum of the all singular values, right? Square root of the all square values, square of the singular values. So both of them have direct connections with sigma, isn't it? Are the definitions fine? Let me show you from books as well, because so that you get used to with your book. Phase by phase, all of you please check this. Matrix norm starts from here. Okay, matrix vector, and then there are some identities. Up to this much it is required. All of you please take some time. If you have the soft copy of Skogestad, then you can open, okay, and go to the appendix. Monica. if you have the soft copy of Fogester, please open, go to the appendix, check the vector norm and matrix norm. The definitions are there. For induced norm, a proof is also there. After that, the properties are also there. Okay. here I need to specify some of the things because otherwise you will get carry on a wrong notion. Okay, first you write, then I will explain. By looking at these functions, are you getting a hint? That is why I wrote that integration in the sense of Lebesgue different than some other things which we generally solve or which we generally learn since our school days.
Those are discontinuous functions.
If we deal with the set of only continuous functions, like here I have declared that is f belongs to C0. Then what is the meaning of this? C, capital C for the space of all real valued continuous functions. That is C for continuous, this subscript 0 means continuous. Sorry, subscript C0 as a whole means real valued continuous functions. Okay, and then 0 comma infinity means like starting it like extends or it is defined for all the values. Okay, from 0 till infinity. Okay, so now then if we deal with all continuous, all continuous functions, then we don't have any problem in integrating. But then if there are some discontinuities, say for example here at this moment, this is a function which you cannot write it by one expression. Within one expression you will have to write as a two part. Right? Even for this one also here, that is at very low value of t, it is going to almost infinity. Like that point is not covered, it is not a real number. Here, there is absent, there is nothing. So this kind of thing that is now for them. That is, so then you can actually say why you are unnecessarily complicating the things. We just can completely skip all those things. But that may not be. Why? Because like sometimes, say for example, now we are also learning nonlinear, right? In nonlinear, there can be something that is which due to like some unforeseen condition or due to some other things, certain discontinuity has come up. Or it may happen that is when you are testing a nonlinear system subjected to a unit step input. Now unit step means at t equals to 0 it will take a huge transition, that means there the rate of change is infinite, right? For them ultimately we don't know what will be the result of the output, especially if it is a nonlinear system. So in such cases it may not be always that we will be dealing with regular waveforms or well-behaved waveforms. So for such cases, that is how to deal with or how to integrate signals with finite number of discontinuities. While studying the Fourier, you might study the Dirichlet conditions, right? And there, do you remember there one of the conditions was there that is okay, a signal can be discontinuous, but number of discontinuity must be finite, and that to all finite term. Do you remember? While studying the Fourier transform, that is for which kind of signals you can take the Fourier transform. Please check once after this Dirichlet condition. there are three conditions. One of them is the signal should have finite number of finite discontinuities. It is not that even if the signal has infinite number of discontinuities, then also you can take out the integration. It is not. So that's why if your signal has finite number of finite discontinuities, then all of you please listen to that is the integration which we do, that means from class 2 level whatever we have learned, that is mostly the concept was given by Newton and not Lagrange, sorry, Leibniz. It's Leibniz. After that came, that is the Riemann, because in Newton's era, still that is at 1965, and then after that, when 1665 up to 17th century, or at the beginning of 17th century, everything was due to the Newton and Leibniz. But the mathematician after them have realized that not all waveforms are purely continuous. There can be this type of things. So then gradually after that, few of the mathematicians that worked on integration, and one of the famous person is the Riemann, who came up with the concept of integrating a class of discontinuous signal, not all, that is impossible, a class of discontinuous signal. But from that, for 1 century it went on really well. But then with the advent of Fourier integral, so for some of the very irregular type of functions, then again it got stuck. And after that, finally, in the about I think 1901, Lebesgue came. He proposed a completely different type of integration theory, which after his name is called Lebesgue integral. So now here, when we define the signal norm, you will find that if we write this calligraphic L1, L2, L, here the integration is in the sense of Lebesgue. So that's why we denote all of them by L1, L2 or infinity. But if you can guarantee, okay, sir, the space of signals with which we will be working, that would be purely C0, then it would be integration simply in the sense of Newton and Leibniz. In that sense, that is, I am saying all those things. That is, if you don't know this, definitely you will have a doubt in whenever you will read from books. Everywhere signal norms means you will find that L1 norm, L2 norm, and infinity norm. And why this capital L has been designated or why it has come? This is the history.
Sir, what has been drawn in the board, all the signals have a value greater than 0, right? Is that because space of all different functions is from 0 to infinity?
No. This is 0 to infinity with respect to the independent axis.
Then why do you draw that f3 to the left half of that? It shouldn't be there, right? Or f3 and f4. All the colors should be on the right half.
So here actually I have considered both the sides, right? That is here, that is C0. You can easily talk about minus infinity to infinity. That too, yes. But for most of since we are going to deal with the systems and causal systems, for them whatever signal we will be getting, they will be all right-handed signals. But this is not directly related to that one. Here I wanted to tell you that is for all of them our Newton-Leibniz integration concept would be applied. But if it is at F4, F5 axis, there we will get stuck in that sense. So F1, F2 belongs to C0, 0, infinity. F3 that belongs to C0 minus infinity, infinity. Okay. Thank you, Arito. That is unknowingly, that is, I drew that, but I didn't anticipate that it can create a confusion. And for F5, F6, F4, they don't belong to C0, right? So now that is, although that is we don't know, that is the Riemann integration is also like little bit complicated in the sense that since we never had those mathematics courses, that's why we feel tough. Otherwise, if it is taught, everything is like possible to understand. So, but anyway, you at least now know the history. So, for Newton-Leibniz, that is, it continued for 1665 to 1710 almost. After that, maybe in between there was another mathematician, Weierstrass. So he started at the early 1700. He also proposed a lot, but after that, that is based on his derivations and the other thing only. Then Riemann came. That is, and Riemann under the guidance of Cauchy. Both of them, they proposed. That is probably in the early 1800th century. So when it was Riemann, I think early 1800. Then when Lebesgue came, it was 1901. And till now, that is Lebesgue integration is continuing. So that is the history of the integration. And here the norm, that's why we always use L. And that's why, that is whether the function is continuous or it has some discontinuities, we don't bother about. So this is for F1, and if it is F2, that is for the, if it is a vector. I am coming to that. First I am writing for all scalar signals. After that, if you have suppose a vector signal, then what will you do? Then you have to do it channel by channel. That's why the summation comes. If some of you are interested in mathematics, you can tell me, I can take separate classes after the mid-sem. All these are like the few of the things which comes from functional analysis, they are really very interesting. Don't think they are tough. It is not tough. We never had those courses, that's why we feel tough. The summation is required. Suppose you have a vector of the functions e to the power minus t, then t into e to the power minus t, e to the power minus 5t. Now, if somebody asks you that if this is a vector, okay, suppose this is my f, I put a underscore to denote it's a vector. If it is book, you will find they will write in a boldface. Here I cannot write boldface, that's why I am putting an underscore. Now, if somebody asks you, you find out the L1, L2 or L infinity norm, then what will you do? Whatever I have written, that is with respect to a scalar signal. But if it is a vector, I cannot simply write this, right? Then this, the same thing I'll have to extend, or I'll have to apply channel by channel. Then we need a summation. That is the reason. Okay. So before writing that, that is, let us define F2. Please tell me how we can write 0 to infinity. If it is soup, how can I write? Now here I cannot write max. Here I have to write soup. Supremum over T. This is what L infinity norm. If these three definitions are clear to you now, can I say that Biot stability is nothing but L infinity stability? I pose this question for all of you. If this three, especially this one, is clear to you now, then can we say that Biot stability, like bounded input, bounded output stability, is nothing but L infinity stability?
L infinity would be bounded.
L infinity means there we are talking about the supremum value or the maximum value. What does Biot mean? Bounded input, bounded output. That means if you for all bounded inputs, the output should also be bounded. Now, if you check out the meaning of the term bounded, bounded in the sense of magnitude or amplitude, nothing but L infinity now. That's why Biot stability is nothing but L infinity stability. Are you getting? That is in the so far what whenever that is we talked about boundedness. Boundedness in which sense? That is a peak, not only the peak value, that is the maximum value beyond which the signal cannot go. So that is with respect to the magnitude or the amplitude. That is nothing but your related to L infinity now. Okay, let us take a small break. After that we will start. Then immediately after this we will go to the system now. So H infinity now we have studied. Today we will learn another interesting thing, H2. This one. Suppose this is a sequence. Okay. This is a sequence. If you add that one, that means if now considering the series version of this sequence, then ultimately what would be the value? We know that it is going to be 2. But is that that element, the final value 2, is that included in this set? So if somebody asks you that if you find out the maximum of that series or of that of the entire set, then there is that 2 value we cannot find. So that is the here, that is what I should have written.
Maximum should be 1, right?
No, actually what I wanted to mean, that is 1, then 1.5, 1.6, 1.7, 1.8, 1.9, 1.99, 1.999, so on so forth. This one is a better one here because there you have to consider first the sequence, then the series version. So in that this is a better example. This one what I wanted to mean, like if you consider a sequence, suppose x n, where it is 1 by n equals to 1 to infinity, that is 1 then half, in that way it will continuously go on. Well, that is the sequence. If you consider this series means then you have to sum up the values. That is the thing which I wanted to mean, but I was not clear enough, that's why it raised a confusion. Anyway, you now consider this set of numbers, 1, 1.5, is go on. Now if somebody asks you that is what is the maximum value, here the maximum is not defined because it is not ending here. If someone says that is 1.9999 is the L, someone else can say that is no, 1.10 number of 9s will be there. So in that way the value is increasing, although at a very small rate. And then that is if you what would be the end point, then that is what would be the limiting value. If this is a set, limiting value would be 2, but that is not included in this set. So in that case maximum is not defined and the supremum would be 2. So that is the main difference between maximum and supremum, is that for an element to be maximum, element of course we are defining or we are discussing over a set of real numbers, then the maximum means that element has to be a part of that set. But supremum may or may not be a part of that set. That is the difference, okay? And if you wish to have a geometric feeling or a real intuition, then this is the concept of supremum, where it is at t tends to infinity, it is going to reach that value, but as you know that infinity means we don't know, that is ultimately when it would reach the value. That's why it is called a supremum, okay? Similarly, the same thing is said for the case of minimum and infimum. One is the sup and max, another one is the inf and min. Okay, the same relation. We will now start system. Okay. Can anybody remember Parseval's theorem? We would be needing Parseval theorems while writing the H2 norm. That relation. First of all, we have to define H2 norm, and then we will find out a relation through which we can numerically find out the H2 norm. For that, we would need Parseval. What is the main principle? Conservation of energy. That is, whether you calculate the energy from the time domain perspective or from the frequency domain, for the same signal the energy should remain the same, right? So that when you have a signal in the square of the signal, here it is complex conjugate transpose. For real valued signal it is same as transpose. Now suppose if it is a square signal, then f star into f means simply that is mod of f whole square. That is, this is amounts to mod of f square. So that means that will give you the instantaneous power contained in that signal, and when you integrate over 0 to infinity, that will give you the energy. So for a real valued signal, the energy content that either you calculate from the time domain or from frequency domain, that must remain the same, and that is nothing but Parseval's theorem. Okay.
Parseval's theorem basically is for defining the energy signal.
That is this time domain energy and the frequency domain energy, they are identically, that is the relation of 1 by 2 by integration. So sorry, this one must be minus infinity. Please make that correction. This is 1 by 2 by integration minus infinity to plus infinity. Okay. So this relation was established in the Parseval's theorem, and the main basis is that the energy will remain the same whether you calculate from the time domain or from the frequency domain. And here I have considered all causal signal, that's why it is from 0 to infinity. If you wish to represent it in a generic sense, here also you can write minus infinity to plus infinity. Whenever you see in the time domain we are writing 0 to infinity, that means we are handling only causal signals, okay? But in the frequency domain, certainly you cannot write 0 to infinity. Why? Because even for causal signal also, in the frequency domain you will find a conjugate spectra or an analogous spectra for the negative frequencies, right? And now now, so this is for the possible theorem. This we will need now, that is we are going to define the H2 norm of a system. This we are now going to find. Okay. Now the system is GS, so that is in the, we are first like starting with the time domain. Okay. So then in the time domain, how do you handle a system? Of course, you have to deal with the impulse response. Impulse response is nothing but again a signal, right? So now there is at this moment, it can be a scalar, it can be a matrix as well. Like it depends upon whether GS is a scalar system, a Sisson system or MIMO system. Accordingly, the dimension of GT will be decided. I am writing small GT in the sense this is just the like standard notation for impulse response, but it can be a matrix as well. Okay. So now that is how the H2 norm is defined. Yes, defined. That will have to understand. That is root over the trace of integration please note that the trace goes off if this is a scalar. Okay.
So if it is a matrix, then we are doing it by element wise, right?
Square root of the trace of integration whole thing. Okay. So now that is, can anybody tell me that is when we had GS equals to C into SI minus A inverse into B. I am considering D to be 0. Now that what will be then GT? Laplace inverse, then what will be that expression? C into C and B will remain the same. In between, what will be C into e to the power 80 into B, right? from the frequency domain also we can do the same thing. Okay. Now that is one thing can you do. That is, you see here there is I started with G transpose or G star G. If it is G star, then also you will be getting a similar thing. But in that case, instead in place of B transpose B, you will have C and C transpose, and here you will have B transpose, isn't it? Please do that. That is another expression.
So here the matrix could be the conjugate transpose, only transpose of it.
Like here I have written in the sense, because in the frequency domain it is going to be star. So in here this star and the simple transpose remain the same because we are dealing with real valued signals. Okay.
there should be a C transpose.
Now here immediately we will ask that is, sir, okay, this derivation we have understood, but really this is going to be impossible to find out this integration, right? If it is for 2 by 2, still that is manageable, but for higher order, that is almost impossible. So that is, we have to do something for finding out this, right? Any idea? Those who had linear system theory, you learn controllability Gramian, observability Gramian. Don't you see that is one of them is controllability Gramian, other one is observability Gramian? Which one?
This one is controllability.
This one, right? And this one is observability Gramian. So this can be found from the Lyapunov equation. Don't worry, those who don't know, I will teach. Don't worry. At this moment, since they had, so that's why I refer to that. What is Gramian, and we will define. V is controllability Gramian, right? These are the main important results. Like Lyapunov equation means many of you know that we often write PA plus A transpose P equals to minus Q. Now Q is not only that Q will always be positive definite, it can be positive semi-definite. It can be positive semi-definite as well. Now in one cases the C transpose C, that is a Q candidate. In other case then PB transpose, that is a Q candidate. And the remaining things in the same. So in the Lyapunov, this is one form, PA plus E transpose P equals to minus Q. Another form also exists, which is AY plus YA transpose equals to suppose some other value, minus Q. So this is one form, this is another form. This is Lyapunov form 1, this is Lyapunov form 2. And both of them are equivalent to each other. So here the Q change maybe this Q prime, the same Q will not work. Are you understanding? So this Lyapunov PA plus A transpose P equals to minus Q. This form is known to many of you. That is called the standard Lyapunov equation, right? A standard Lyapunov equation when applied to control theory. Now, if you see this one, so this is like for controllability Gramian and observability Gramian, they have a special property of satisfying these two particular Lyapunov equations. That is this Q, that is the solution, like P has been replaced by Q. So where this P is the Lyapunov candidate with that is the solution we search for. Here Q is that solution which we will try to find. So here as if this is PA plus A transpose P plus Q. So instead of P, here I have used Q, and they are originally the Q candidate, that is here C transpose C. Please don't get confused between that Q and this Q. If you have a confusion, then in place of this Q you can write U or something, okay? Now this is the solution. So this observability Gramian Q, that is the solution to this Lyapunov equation. That is Lyapunov equation with that matrix being C transpose C. That means with the Q matrix being C transpose C. You check the dimension. But what will be the dimension of C? P cross N. So C transpose C means N cross P into P cross N. So it will give you N cross N. Because always Q and A, both of them N cross N. So here whatever may be the candidate, its dimension must be N cross N. That one should always be careful of. Similarly here also AB plus BA transpose, you see that form is the second one. Y plus YA transpose equals to minus Q prime. Here also the same thing, AB plus BA transpose plus BB transpose equals to 0. Now what is the dimension of B? N cross N. So N cross N into M cross N. So as a whole, it will give you N cross N. Okay? On that is like next day or even that is I will give you two problems. I will give you one picture. Okay? So because now we don't have time. So from this definition, what you have understood? Like first of all, whether you find it in the frequency domain or in the time domain, they are the same. See, if you wish to calculate it in the frequency domain, then here you have the scaling factor 1 by 2 pi. That everything is in the frequency domain, right? But the same thing now, if you wish to express in time domain, then for that actually we will have to exploit Parseval theorem, and that is the reason why at the beginning I said that is here we use Parseval theorems. Now here only that is you could mark one difference compared to this definition. Here straight away I started from keeping the trace outside, and now here why this is happening, because this is a linear operation. And what is this integration, when it is on a matrix, it is a linear operation, and that is the reason why I can take out the trace out. And here also that is you can ask that is sir, how could you directly pull out the C from there, because C first of all is a constant matrix, right, and the integration is with respect to T. So that's why that is I have that is kept this entire bit in between. Here that is B transpose, that is also, like B is also a constant matrix, but certainly I cannot pull out B because that is in a punch situation in between e to the power at and e to the power a transpose t, right? And this whole thing, integration 0 to infinity, that whole bit is called that Gramian part. That is one thing, that is the controllability Gramian and the observability Gramian, okay? But I believe that is some of you don't know the concept of this controllability Gramian, observability Gramian. That we'll have to learn. Anyway, at this moment we are learning the calculation part. From our exam point of view, mainly the calculation part would be required. But for the Gramian, because the intelligent heterogeneous system theory, for that I will teach. Don't worry. But now that is, can you see that is how that is we have defined the H2 norm? You see, it is more or less the same as that of L2 norm. But now it is a system, right? Because if you see the frequency domain object, that is not just a signal, that is a system. Also, that will be an object of a Hardy space. Although from the time domain perspective, it seems to be just a real valued signal, but you go to the frequency domain, then it is not a frequency domain, it is not just a like function space, it is rather a Hardy space, okay? That is the space of all holomorphic functions. So for that, now this is the derivation. So the H2 norm of a system, it can be derived or it can be calculated either based on V or Q. It is completely your choice. Because anyway we would be needing ABC, okay? And now if it is a first order or second order system and scalar, for that hand-driven calculation is sufficient, we can do. But if it is a higher order system or if it is like MIMO system, then hand-driven calculation is really difficult. For that we need to take the help of this controllability Gramian and observability Gramian. Now here lies an interesting question. If you remember that when I defined that H2 norm, and especially RH2 space, then I said we need, that is a space of all real, rational, strictly proper, asymptotically stable transfer function. I specifically mentioned that is for this H2 norm to be finite, we need the D equals to 0. Now the full integration is in front of you. Can anybody tell me why D is supposed to be 0?
Otherwise, if D is there, then
That component will give you an infinite contribution.
0 to infinity d.
Exactly. Even in omega also the same thing. That is the reason. At that time, if you remember, I said that it will be clear later. This is the reason. That is, RH2 space means for all those objects, H2 norm must be finite. Now from this integration, it is clear to all of us that here, if you have a constant term here, suppose if you have a constant term here, D, then ultimately that will contribute to an infinite sum, right? So that means H2 norm is going to infinite. So that means that doesn't exist, not a real number. That's why for all the transfer functions to have a finite H2 norm, D must be 0. And D0 means it is a strictly proper transfer function. Okay. For biproper transfer function, there no problem with respect to H infinity norm, but certainly H2 norm is infinite. Whether D is minus or plus, that doesn't matter. When you integrate, finally that will go to infinity. Is it now clear? So RH infinity, that space means the space of all real, rational, proper and asymptotically stable transfer function matrices of dimension m cross m. And if it is RH2, only there will be one change, the space of all real, rational, comma, strictly proper and asymptotically stable transfer function matrices. Okay? I just give you a small problem to solve here. Suppose the system description is given by this ABCD. Okay, then what would be the two norm of that system?
এবার পরীক্ষায় ভুল কোশ্চেন দিয়ে দেবে না
ভুল কোশ্চেন
ডিস্টেন্স ফিল্টারের মতন কন্টিনিউটি ম্যাট্রিক্স rank is less than the full rank for the Lyapunov step for Lyapunov step question পর পর দুটো
ওটা সেম কোশ্চেন ছিল না, ওটা আলাদা কোশ্চেন ছিল। আমাদের যদিও এক্স্যাক্টলি খেয়াল করছে না, কিন্তু ওটা দেখতে সেম বাট অ্যাকচুয়ালি আলাদা।
এই নাম্বার শুধু আলাদা ছিল, স্টেটের যে ইয়েটা জায়গাটা ছিল ওটা জাস্ট একটা 10 0 20 0 এরকম কিছু ছিল, জাস্ট নাম্বারটা চেঞ্জ ছিল, পজিশনগুলো একই।
হ্যাঁ, কিন্তু তার মধ্যে ওটা তোমরা ওই 6 নম্বরের কোশ্চেনটা বলছো তো? আমি আরেকবার দেখে আজকেই বলে দেবো যে কোথায় ডিফারেন্সটা ছিল।
কোনো ইউনিকলি আসছে না।
ও লিয়াপুনোভেরটা, তাহলে 2 নম্বরেরটা বলো। হ্যাঁ, ইউনিক কি করে আসবে? ওটা ভুল ছিল না।
আনকন্ট্রোলেবল ছিল।
হ্যাঁ, ওটা ওইখানেই মানে লিখে দেওয়া উচিত ছিল যে ওটা আনকন্ট্রোলেবল সিস্টেম। In case of Lyapunov, one thing is that if it is not controllable, but in that you only the A matrix was required, right? It was not related to controllability. Probably one question was there which was related to state feedback design.
Now we have to check if the system is stable or not.
Huh. Now,
in that case we have to check for like if there exists a Q,
huh.
for a unique Q there should be exist a P.
Exactly. Now that conclusion or that result, that is for only asymptotically stable cases. Now, if the system is not asymptotically stable, then what will happen? That is, either you don't find an unique P, or there will be, it is multiple solutions may be possible. So it was related to that only. Like the original system for which the API provided or the AI provided, that was probably 0100. So it was not a faulty question. It was, that's what that is. It was expected that is you will write that is no. That in this case that is, we don't find any unique P against any unique Q.
So if it is less, the rank is less than the full rank, then from that we can conclude that it is not there shouldn't exist a unique solution.
In case of Lyapunov, you will have to show that whether there exists a positive definite P. Now, positive definite P means either you check the rank of that matrix, or it is eigenvalues you will have to check. If the matrix is symmetric and both of them are positive eigenvalues, then that is a positive definite matrix. Now, in those cases, you will find that is you cannot find a positive definite P. There itself you will get stuck. Okay. Now last day we were discussing SVD. I told you that is I will just mark you some page numbers or a problem, right? So this SVD and how that is important to control theory, for that is in Swamp Pogester book, page number 68 to 85, okay? 68 to 85. In between, that is, you will find many things related to SVD and its illustration. Some other things are also there, those are not required. So that you should study. Please check what are the things there. Directions of a multivariable system, that is important, which will also come from SVD. From 58 to 85. Okay, so there you will
68 to
85.
68 to
Huh. Not everything is required. You will find that is they start with the direction of multivariable systems and then norms of the signal, the gain, and then how you can find out the maximum gain channel or minimum gain channel. Regarding that, the concept of SVD will be used. Then there is a very interesting example of distillation column that is highly required. Probably that is example number 3.5, and then it continued to 3.6. Arun Surya and Vanika, you want to check that from the book. Given, do you have that soft copy? Have you seen it?
Yes, sir.
58 to 85. Okay. So Joshua? Okay.
58
58. 58 to 85. 68 or 58? 68. Sorry. 68. Mostly that if you directly go to example number 3.5 and 3.6, that is the main thing you have to study. The example of distillation column. Few of you asked me that to give an example of a yield condition matrix and when those things are particularly relevant in system theory. So distillation column is an example. There you will find that is in one channel the gain is very high and in the other channel gain is very low. So that for that analysis SVD is really important. And while choosing the input, how you are going to design the input, there you need to first check those information, that is in which direction the gain would be maximized and in which direction the gain would be minimized. Never those things were required for CISO system, but for NEMO definitely those things would be required. Okay, alright, খালি এর বইটা তোমাদের কাছেই রেখে দাও, স্যার দরকার তোমাদের রস করে নিও, তুমি তোমার